October 19, 1944, Rechlin Airfield, northern Germany. Hauptmann Dietrich Werner stood beside the most unusual aircraft to arrive at Germany's premier aviation testing center in months. The fighter before him bore Japanese markings hastily painted over with Luftwaffe crosses. Its distinctive inverted gull wing and massive radial engine cowling made it unmistakable. This was a Vought F4U Corsair, America's frontline naval fighter, and it had travelled nearly 7,000 miles from the Pacific Theatre to this airfield 100 kilometres northwest of Berlin. Werner had flown nearly every German fighter type during his career as a test pilot. He had evaluated captured Spitfires, P-38s, and P-51 Mustangs. But the Corsair represented something different. This was the fighter American naval aviators used to dominate Japanese Zeros. Intelligence reports described it as the most powerful single-engine fighter in operational service anywhere in the world. Its Pratt Whitney R-2800 double Wasp engine produced over 2,000 horsepower, more than any German fighter engine could generate. The aircraft before Werner bore serial number 17,752. It had been manufactured by Vought in Stratford, Connecticut, in March 1944. After completing carrier qualification trials, it was assigned to Marine Fighter Squadron VMF-214 operating from Peleliu Island. On August 23, 1944, Second Lieutenant James Morrison had been escorting SBD Dauntless dive bombers attacking Japanese positions on Bab el-Thuab when his engine suffered catastrophic oil pressure loss. Morrison managed to ditch in shallow water near a small island he believed was unoccupied. It wasn't. Japanese naval infantry recovered Morrison and his aircraft. The pilot became a prisoner. The Corsair, damaged but largely intact, became an intelligence prize. Japanese technicians at Truk, Atoll's naval base, spent 3 weeks repairing the fighter. They were particularly interested in the R-2800 engine, which significantly outperformed anything in Japanese inventory. But Japan's deteriorating strategic situation and limited testing infrastructure meant comprehensive evaluation was impossible. In September 1944, the Japanese Navy offered to transfer the captured Corsair to Germany via submarine. This was part of broader, though largely unsuccessful, Axis technical cooperation. The submarine I-29 departed Truk on September 8, carrying the Corsair's engine, propeller, key components, and complete technical documentation. The airframe itself would follow by a different route. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The I-29 never reached Germany. American submarine USS Sawfish torpedoed and sank it in the Philippine Sea on October 10th. But through extraordinarily complex logistics involving neutral ports and diplomatic channels that remain partially classified even today, the Corsair airframe did reach Europe. By mid-October 1944, it sat at Rechlin, awaiting systematic evaluation by Germany's best test pilots and engineers. Rechlin-Las Airfield had served as the Luftwaffe's primary aircraft testing and evaluation center since the facility's secret reopening in 1922. The Treaty of Versailles had prohibited German military aviation, but the Weimar Republic maintained Rechlin clandestinely for exactly this purpose. By 1944, Rechlin encompassed multiple sites, including the main grass-surfaced airfield, satellite facilities, and extensive laboratory complexes. The installation employed over 2,000 personnel, test pilots with thousands of hours evaluating every German aircraft type. Engineers with doctorates from Berlin, Technical, University and Göttingen. Technicians trained to extract precise performance data from test flights. Rechlin's mission was comprehensive evaluation of every new Luftwaffe aircraft design and thorough analysis of captured enemy aircraft. The facility had tested dozens of Allied aircraft types since 1940. British Spitfires, American P-38s, Soviet Yaks, and large EGs. Each evaluation produced detailed technical reports distributed to Reich Air Ministry officials, aircraft manufacturers, and operational commanders. These reports were considered the gold standard throughout German aviation. Favorable assessments from Rechlin could secure lucrative production contracts. Unfavorable reports could doom development programs. The captured Corsair's arrival generated immediate interest. Intelligence reports from the Pacific described the F4U as possessing exceptional performance at all altitudes. Japanese pilots reported being unable to escape pursuing Corsairs through traditional evasive maneuvers. The fighter's speed, climb rate, and diving performance exceeded everything Japan could field. German engineers wanted to understand exactly how American designers had achieved such capabilities. Before test flights could begin, Rechlin's engineers needed to comprehend every system aboard the Corsair. This proved challenging. The F4U represented naval aviation design philosophy, significantly different from German land-based fighter development. The aircraft was massive by German standards, weighing over 9,000 pounds empty and nearly 14,000 pounds fully loaded. For comparison, a Messerschmitt Bf 109 G6 weighed 5,900 pounds empty. The Corsair weighed as much as 2 German fighters, yet flew on a single engine, producing power levels German designers had never achieved in operational service. The distinctive inverted gull wing immediately drew attention. German engineers recognized this as an elegant solution to multiple take-time problems. The design allowed shorter, stronger landing gear while maintaining propeller ground clearance. The wing root met the fuselage at 90 degrees, minimizing drag at the junction. The configuration provided excellent pilot visibility over the nose during carrier approaches. Oberingenieur Klaus Hartmann, Rechlin's chief structures engineer, spent days examining the wing. His report noted sophisticated stress analysis and careful attention to weight distribution. The wing was incredibly strong, designed to withstand carrier landing impacts that would destroy land-based fighters. Yet it wasn't unnecessarily heavy. American designers had calculated loads precisely and engineered structures to exact requirements. The cockpit arrangement reflected naval operations priorities. The seat was positioned high in the fuselage, providing exceptional visibility. The canopy offered nearly unobstructed views in all directions except directly aft. Instrument layout was logical but different from German practice. American instruments used unfamiliar calibrations. Every switch and control required identification before flight testing could begin. The most impressive feature was the engine. The Pratt Whitney R-2800 double wasp was a masterpiece of American engineering. This 18-cylinder, 2-row radial engine represented the culmination of decades of American radial engine development. In standard configuration, it produced 2,000 horsepower at takeoff. With water methanol injection, which the captured Corsair possessed, output increased to approximately 2,250 horsepower. German engineers familiar with the BMW 801 radial powering the Focke-Wulf FW190 recognized similar basic architecture. But the R-2800 was significantly larger, substantially more powerful, and considerably more sophisticated. They carefully documented every visible feature: the 2-stage, 2-speed supercharger, the sophisticated fuel injection system, the complex ignition system with dual magnetos, the precision-manufactured cylinder assemblies. What impressed German observers most was manufacturing quality. Every component showed precision workmanship with consistent tolerances. Bearings were ground to specifications. German industry struggled to maintain under bombing and material shortages. Every fastener was correctly sized and properly installed. The engine showed no manufacturing shortcuts, no substitute materials, no cost-cutting compromises. Diplom-Ingenieur Werner Oswald, a Daimler-Benz engineer temporarily assigned to Rechlin, examined the R-2800 exhaustively. His preliminary report noted that the American engine demonstrated engineering sophistication matching or exceeding Germany's best aero engines. The supercharger installation particularly impressed him. The 2-stage system with intercooling allowed the engine to maintain high power output at altitudes where German fighters struggled. The armament installation revealed American firepower doctrine. The Corsair carried 6 Browning M250 caliber machine guns, 3 in each wing. This represented devastating firepower concentrated in a stable gun platform. German engineers calculated that all 6 guns firing together delivered approximately 17 pounds of projectiles per second. A Bf 109 G6 with one 30mm cannon and two 13mm machine guns delivered approximately 7 pounds per second. The American installation philosophy prioritized maintainability. Each gun could be accessed through large panels, requiring only simple tools. Ammunition boxes held 2,400 rounds total, providing approximately 25 seconds of firing time. German cannon-armed fighters carried perhaps 60 rounds per gun, requiring strict fire discipline. The Corsair pilot could fire longer bursts with less concern about ammunition exhaustion. Structural analysis revealed engineering conservatism reflecting carrier operations requirements. The F4U's airframe used heavier gauge aluminum than comparable German fighters. The structure was significantly overbuilt by German standards. Everything was designed to withstand repeated carrier landing stresses that would destroy conventional aircraft. The landing gear was massively strong, with shock absorption capabilities far exceeding land-based fighters. The hydraulic system impressed German engineers with its sophistication and redundancy. Landing gear retraction, flap operation, brake actuation, and cowl flap control all used hydraulic power. The system incorporated multiple backup features. If primary hydraulic pressure failed, emergency systems allowed gear extension by gravity and manual backup. German fighters typically relied on simpler mechanical or electrical systems with fewer backup options. After 3 weeks of ground examination, Reschlin's test pilots prepared for first flights. The captured Corsair, now painted in Luftwaffe colours with prominent recognition markings, sat on Reschlin's grass airfield awaiting its first German pilot. Initial test flights would focus on basic handling, takeoff characteristics, climb performance, level flight at various altitudes, simple maneuvers, and landing. The test pilot assigned to the first flight was Hauptmann Dietrich Werner. Werner had logged over 3,000 hours in fighters ranging from early Bf 109s to the latest FW190D models. He was considered one of Reschlin's most experienced and analytical pilots. His reports were noted for precision and objectivity. Werner approached the Corsair with professional curiosity tempered by caution. This was an unfamiliar aircraft with unique characteristics. The first impression upon entering the cockpit was exceptional visibility. The high seating position provided unobstructed views forward and to both sides. The canopy framing was minimal. Werner could see more of the surrounding airspace than from any German fighter he had flown. This visibility advantage would be significant in combat, where seeing the enemy first often determined survival. Starting the R-2800 required following careful procedures documented during ground testing. Werner engaged the fuel boost pump, set mixture to rich, cracked the throttle slightly, and activated the starter. The massive radial coughed, backfired once, then caught with a deep roar that shook the entire airframe. As the engine warmed, Werner methodically checked each system. Oil pressure stabilized quickly. Cylinder head temperatures rose normally. All gauges indicated proper function. Taxiing revealed the first significant handling characteristic. The long nose completely obscured forward visibility on the ground. Werner had to S-turn continuously to see ahead, swinging the nose left and right to check for obstacles. This was dramatically different from German fighters with relatively short noses. But the wide-track landing gear made ground handling exceptionally stable once Werner adapted to the visibility limitation. The takeoff run surprised Werner with its brevity despite the aircraft's weight. 2,000 horsepower accelerated the Corsair rapidly. The tail lifted naturally at approximately 40 miles per hour. Forward visibility improved dramatically. At 75 miles per hour, Werner eased back on the stick, and the Corsair lifted smoothly from the grass. The gear retracted cleanly. Werner trimmed for climb and advanced the throttle to climb power. What happened next would fundamentally challenge German assumptions about fighter performance. The initial climb was where German expectations collided with uncomfortable reality. Preliminary calculations based on the Corsair's weight suggested good but not exceptional climb performance. The actual performance exceeded every prediction. More disturbing, as altitude increased, the Corsair's climb rate remained extraordinarily strong, far longer than German fighters could match. Werner maintained a steady climb, carefully monitoring engine instruments and noting altitude, airspeed, and time. At 5,000 feet, the vertical speed indicator showed approximately 3,800 feet per minute. A Bf-109 G6 at similar weight could manage approximately 3,900 feet per minute. The German fighter was marginally superior at low altitude, as expected. At 10,000 feet, the Corsair was climbing at 3,600 feet per minute. The Bf-109 would achieve approximately 3,600 feet per minute at this altitude. The fighters remained comparable, but at 15,000 feet, something remarkable became apparent. The Corsair maintained 3,400 feet per minute, while the Bf-109's rate degraded to approximately 3,000 feet per minute. At 20,000 feet, the performance gap widened dramatically. The Corsair climbed at 3,200 feet per minute. The Bf-109 managed only 2,200 feet per minute. The American fighter was climbing nearly 50% faster at operationally critical altitudes. At 25,000 feet, the disparity became crushing. The Corsair sustained 2,900 feet per minute. The Bf-109 struggled to achieve 1,600 feet per minute. Werner continued climbing, astonished by the Corsair's sustained performance. At 30,000 feet, the fighter was still climbing at 2,500 feet per minute. At 35,000 feet, it maintained 2,000 feet per minute. The service ceiling appeared to be near 40,000 feet with usable combat capability. German fighters could barely reach 38,000 feet with virtually no combat effectiveness at such altitudes. This high-altitude performance confirmed the most troubling intelligence reports from the Pacific. The R-2800's two-stage supercharger provided decisive advantage that fundamentally altered combat dynamics at operationally important altitudes. The traditional German tactic of climbing above enemy formations was neutralized when the enemy could climb higher with superior performance at altitude. Werner began level flight testing at various altitudes. At sea level, the Corsair achieved approximately 355 miles per hour in level flight. This was respectable but not extraordinary. German fighters were competitive at low altitude, but as altitude increased, the performance gap widened systematically. At 15,000 feet, the Corsair reached 405 miles per hour. At 20,000 feet, it achieved 420 miles per hour. At 25,000 feet, 427 miles per hour. At 30,000 feet, where bomber escorts operated most frequently, the Corsair reached 433 miles per hour. German fighters struggled to exceed 380 miles per hour at similar altitudes. This 50-mile-per-hour deficit translated to tactical disaster. The slower fighter could neither catch the faster opponent nor escape pursuit. Combat occurred at the faster fighter's discretion. The diving performance exceeded even Werner's elevated expectations after experiencing the climb capability. He put the Corsair into a 30-degree dive from 25,000 feet. The aircraft accelerated smoothly and controllably. At 20,000 feet, indicated airspeed showed 460 miles per hour. At 15,000 feet, 520 miles per hour. At 10,000 feet, over 570 miles per hour. Werner began recovery, noting heavy but effective control forces. The Corsair transitioned smoothly back to level flight, with no concerning compressibility effects or control difficulties. German fighters could dive quickly, but not with this combination of speed, control authority, and structural safety. The Bf-109's wing generated severe compressibility effects at high speeds, making recovery dangerous. The W-190D was better but still developed control problems. The Corsair could dive with near impunity. This meant German fighters could no longer safely disengage by diving away, a fundamental tactic that had saved countless German pilots' lives against other Allied fighters. Any engagement with a Corsair would be fought until one aircraft achieved victory, or the American pilot chose to break off. German pilots would have no safe escape option. Maneuverability testing revealed expected trade-offs. The Corsair's weight and wing loading meant it couldn't sustain tight turns with lighter German fighters. In slow-speed turning combat, a Bf-109 or Fu-190 would eventually gain advantage through superior turn radius. But Werner noted the Corsair's exceptional roll rate. At speeds above 250 miles per hour where most combat occurred, the Corsair could reverse direction through rapid aileron rolls faster than German fighters could turn. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. While it couldn't sustain circular turns indefinitely, it could maneuver effectively using high-speed direction reversals. This gave experienced pilots tactical options that negated the turn rate disadvantage. More importantly, most combat would occur at altitudes where the Corsair's power advantage allowed it to dictate engagement terms. German pilots wouldn't get opportunities for sustained turning combat unless the American pilot made errors. Maximum altitude testing produced perhaps the most strategically troubling results. Werner climbed systematically on subsequent flights. At 35,000 feet, the Corsair remained highly responsive with adequate power for combat maneuvers. At 37,000 feet, the aircraft could clearly operate effectively. At 39,000 feet, performance remained sufficient for interception missions. The test report noted combat capability at 37,000 feet exceeded what German fighters achieved at 32,000 feet. German fighters struggled to reach 38,000 feet, arriving with virtually no combat capability. The Corsair operated comfortably at similar altitudes with enough performance reserve for aggressive combat. American bombers typically flew at 24,000 to 28,000 feet over Europe, higher over Japan. The Corsair could escort them while operating 10,000 to 12,000 feet above, providing enormous tactical advantage. Armament testing demonstrated the devastating firepower. Intelligence reports described all 6 50 caliber machine guns functioned flawlessly. A 1-second burst placed approximately 85 rounds into the target area. The volume of fire was impressive. The accuracy from a stable gun platform was equally impressive. Werner noted that the Corsair's size and weight made it an exceptionally steady gun platform. Lighter fighters experienced more disturbance from gun recoil. What most impressed German observers was ammunition capacity. With 2,400 rounds total, the Corsair could fire for approximately 25 seconds of continuous trigger time. Realistically, pilots would use shorter bursts, extending ammunition to dozens of firing passes. German cannon fighters carried perhaps 200 rounds, requiring extreme fire discipline. 1 or 2 firing passes expended most ammunition. The tactical implications were profound. A Corsair pilot could afford to take multiple shots at difficult targets. A Bf-109 pilot with 60 rounds of 30mm ammunition had perhaps 3 firing opportunities before returning to base. This disparity affected combat aggressiveness and risk calculation. The Corsair pilot could be patient and selective. The German pilot faced constant ammunition anxiety. Durability testing came next. Though German engineers could only simulate combat damage rather than observe actual battle results, the structural analysis suggested extraordinary resilience. The massive R-2800 radial engine provided significant protective shielding for critical systems. The aircraft's substantial size meant separated and often duplicated vital systems. Loss of one system didn't necessarily compromise flight capability. Ground tests simulated various damage scenarios. The Corsair could sustain significant tail surface damage and remain controllable. It could lose multiple cylinders and continue flying. The self-sealing fuel tanks worked effectively. The entire philosophy emphasized pilot survival and aircraft recovery. Every design choice reflected understanding that naval aviators operating over vast ocean expanses needed aircraft capable of returning to carriers despite damage. The systems analysis revealed manufacturing sophistication that German industry could no longer consistently match. Every component showed precision manufacturing and quality materials. Bearings were precision ground. Every fastener was correctly specified. Wiring harnesses were professionally assembled with proper strain relief. The aircraft showed no manufacturing shortcuts, no substitute materials, no evidence of wartime quality degradation. This suggested industrial capabilities that German engineers found deeply concerning. The Corsair was complex and expensive to build, yet Vought, Goodyear and Brewster were producing these aircraft at combined rates exceeding 100 per month by late 1944. The engineering sophistication, manufacturing quality, and production rate simultaneously suggested an industrial system operating at levels Germany could not approach. After 6 weeks of intensive testing through November and early December 1944, Rechlin produced a comprehensive evaluation report. The document was classified Geheime Kommandosage, distributed only to the highest command levels. The assessment was extraordinarily blunt. The F4U Corsair represented the most capable single-engine fighter the Luftwaffe had evaluated, combining exceptional high-altitude performance with devastating firepower, robust construction, and operational characteristics superior to any German fighter in service or development. The report identified multiple grave concerns. The Corsair's climb performance meant American fighters could achieve altitude advantage before engagements. Its high-altitude superiority meant it could choose when and where to engage. Its diving speed meant German fighters couldn't safely disengage. Its firepower meant any aircraft caught in its sights faced near certain destruction. Its structural strength meant it could survive damage that would destroy German fighters. The report recommended urgent development of German fighters capable of matching high-altitude performance, though the authors acknowledged this would require years Germany clearly didn't have. It recommended immediate tactical revisions. Avoid combat above 20,000 feet. Avoid diving as escape tactic. Attack only from overwhelming numerical or positional advantage. Use hit-and-run tactics, prioritizing survival over victory claims. The authors recommended everything except the one thing Germany actually needed: time to redesign its aviation industry and aircraft development philosophy from fundamental principles. But Germany was in its final months, fighting desperately on two collapsing fronts with dwindling resources and vanishing hope. The captured Corsair, after completing its Rechlin test program in early December 1944, was assigned to a specialized Luftwaffe unit that would give it one final mission. Circus Rosarius, commanded by Flugkapitän Theodor Rosarius, operated as a traveling demonstration squadron with deadly serious purpose. The unit's mission was familiarizing frontline Luftwaffe pilots with captured Allied aircraft through hands-on demonstrations that might save German lives. Circus Rosarius operated like a traveling airshow for military audiences. The unit would arrive at fighter bases across Germany and occupied territories with an inventory of captured aircraft, Spitfires bearing Luftwaffe crosses, P-51 Mustangs in German camouflage, P-38 Lightnings with yellow identification bands, and now the distinctive bent-wing Corsair, all repainted in German colors with the characteristic T9 identification code. Experienced test pilots would fly these aircraft through carefully choreographed demonstrations showing capabilities and limitations. Frontline pilots attended comprehensive briefings with performance data and tactical recommendations based on Rechlin testing. Selected pilots sometimes flew captured aircraft under supervision, experiencing firsthand what they would face in combat. This practical education was designed to transform abstract intelligence reports into visceral understanding. The Corsair, repainted in standard Luftwaffe splinter camouflage with bright yellow wing tips and fuselage band identifying it as a test aircraft, bore the code T9+CU. The yellow markings served dual purpose. They prevented friendly fire from German anti-aircraft units, who might mistake the unusual silhouette for an enemy intruder. They also made the aircraft highly visible during demonstrations, ensuring every pilot in attendance could track its movements clearly. When Zircus Rosarius arrived at bases throughout December 1944 and into early 1945, the Corsair drew enormous crowds. Pilots who had heard rumors about the powerful American naval fighter studied it carefully. Maintenance personnel examined the massive engine and sophisticated systems. Younger pilots with limited combat experience received education that might mean the difference between death and survival in their first encounters. Demonstration flights followed carefully scripted sequences designed to illustrate specific tactical lessons. A test pilot would start the R-2800 engine, its distinctive deep roar immediately recognizable. He would taxi out, S-turning to maintain forward visibility, then take off with a short ground roll that impressed observers familiar with heavily loaded German fighters requiring much longer takeoff distances. German fighters, often Bf-109Gs or FW-190Ds, would orbit overhead at various altitudes. The Corsair would climb aggressively toward them. At 10,000 feet, the German fighters and Corsair appeared roughly matched. At 15,000 feet, the Corsair began pulling away. At 20,000 feet, the performance gap was obvious even to observers on the ground. At 25,000 feet, the Corsair was still climbing strongly, while German fighters struggled. This visual demonstration made the data from Rechlin testing undeniable. You cannot outclimb a Corsair above 15,000 feet. German fighters that had dominated altitude combat earlier in the war now faced an opponent that could achieve superior position, regardless of German pilot skill or tactical cleverness. The altitude advantage belonged to whoever flew the Corsair. Then came the diving demonstration. Both the Corsair and a German fighter would begin at 30,000 feet. They would dive together toward the field. Initially descending side by side, the Corsair would steadily pull away. By 20,000 feet, the gap was substantial. By 15,000 feet, the Corsair was hundreds of meters ahead. By 10,000 feet, the German fighter was hopelessly outpaced. The demonstration viscerally communicated what words could not fully convey. You cannot escape a Corsair by diving. The traditional German tactic of diving away from unfavorable combat had been negated. Any pilot who engaged a Corsair committed to fight until one aircraft achieved victory or until the American pilot chose to disengage. There would be no safe escape for German pilots. The turning demonstration provided some encouragement. At lower altitude, around 6,000 feet, the Corsair would engage a Bf-109 or W-190 in turning combat. The German fighter would clearly outturn the American fighter in sustained circular combat. After 2 or 3 turns, the German fighter would be gaining angle. This showed German pilots they retained advantages that proper tactics could exploit. But the briefings emphasized critical context. The Corsair pilot would never accept sustained turning combat unless tactically forced into it. The American fighter's superior climb and dive performance meant its pilot could control engagement terms. He could climb away, he could dive away, he could use high-speed slashing attacks. German pilots might theoretically win turning combat, but they would rarely get opportunities to turn fight unless facing inexperienced American pilots making fundamental tactical errors. Briefings following demonstrations emphasized specific tactics based on comprehensive Rechlin testing. Avoid combat above 20,000 feet where the Corsair's performance advantage was overwhelming. Avoid diving as an escape tactic since the Corsair could match or exceed any German fighter's diving speed. Exploit the Corsair's inferior sustained turn performance through slow-speed maneuvering combat if tactically feasible. Attack from positions minimizing the Corsair's energy advantages, below and behind where the massive engine limited pilot visibility. From directly astern where the American pilot had no rear visibility, from angles preventing the Corsair from converting speed into climbing or diving maneuvers. Engage only with numerical superiority or overwhelming positional advantage. Use formation tactics concentrating multiple fighters against single Corsairs. Make high-speed slashing attacks through formations rather than sustained engagements. Prioritize survival over victory claims. Break off combat at first indication of unfavorable dynamics. The Germans needed their experienced pilots far more than they needed additional kill claims. Major Heinz Baer, a Luftwaffe ace credited with 220 victories who flew against Corsairs in the Mediterranean and evaluated captured examples, provided frank assessments that circulated through Zirkus briefings. The Corsair is the most formidable single-engine fighter the Americans have deployed. It combines the P-51's speed, superior climb performance, heavy firepower, and exceptional structural strength. Fighting Corsairs requires perfect tactical discipline and acceptance that we cannot defeat them through individual combat skill. We must use formations, surprise, and immediate disengagement when conditions turn unfavorable. Hans-Joachim Marseille, before his death in 1942, had demonstrated that exceptional German pilots could defeat numerically superior opponents through superior tactics and marksmanship. But Marseille fought obsolescent British fighters and inexperienced Allied pilots. By late 1944, Luftwaffe pilots faced experienced Allied aviators flying aircraft like the Corsair that negated traditional German tactical advantages. The Zirkus's educational mission became increasingly urgent as Allied numerical superiority grew overwhelming. By early 1945, the unit's inventory included multiple captured aircraft representing the full spectrum of Allied fighter capabilities. But the gap between understanding enemy capabilities and possessing competitive German aircraft to implement proper tactics grew wider daily. German pilots knew theoretically how to fight Corsairs optimally. They understood the tactics that might provide survival chances. But they lacked sufficient competitive fighters, adequate fuel, or enough experienced wingmen to implement recommended tactics consistently. They knew they should avoid high-altitude combat, but Allied bombers flew high, forcing German interceptors to climb where Corsairs and other Allied escorts dominated completely. By February 1945, maintaining the captured Corsair became logistically impossible. The R-2800 engine required high-octane aviation fuel increasingly scarce throughout collapsing Germany. It needed specialized maintenance that German mechanics struggled to provide without proper manuals, tools, or spare parts. The aircraft's complex systems began failing without American spare parts. By late March 1945, with Allied armies advancing from west and east, Zirkus Rosarius effectively ceased operations. Its aircraft were scattered across various airfields. Some were destroyed to prevent recapture. Others were abandoned as fuel exhausted, and German forces retreated. The Corsair's ultimate fate remains uncertain. It may have been destroyed at Bad Wörishofen in Bavaria. It may have been captured intact by American forces. Records from that chaotic period are incomplete, but the captured Corsair's impact extended far beyond its physical existence. American intelligence officers discovered detailed German test reports after the war's end. These documents revealed that German engineers understood Allied fighter capabilities with remarkable precision. The Rechlin evaluation of the Corsair was comprehensive, technically accurate, and strategically insightful. The reports demonstrated that Germany's defeat wasn't caused by failure to understand Allied capabilities. German test pilots and engineers provided accurate assessments. They identified strengths and weaknesses objectively. They developed tactically sound countermeasures. The defeat resulted from Germany's inability to produce competitive aircraft in adequate numbers, train sufficient pilots, or maintain industrial capacity under sustained Allied bombing. The production statistics revealed the magnitude of strategic disparity. Vought Aircraft's Stratford plant produced approximately 400 F4U Corsairs monthly by late 1944. Goodyear's Akron facility added another 300 F2G variants monthly. Brewster's plant contributed additional production until quality problems forced contract cancellation. Combined American production exceeded 600 Corsairs monthly from just two primary manufacturers. Germany's entire fighter production in January 1945 totaled approximately 1,000 aircraft of all types. This included Bf-109s, FW-190s, Me-262s, and various other designs. American production of a single specialized naval fighter type approached two-thirds of total German fighter output. and America simultaneously produced P-51s, P-47s, P-38s, P-61s, and other fighters in vast quantities, while supplying allies and maintaining massive strategic bombing campaigns. Even if German pilots achieved favorable kill ratios through perfect tactics and superior training, basic arithmetic made defeat inevitable. America would simply replace losses faster than Germany could inflict them. The asymmetry was unsustainable and grew worse monthly as German production declined under bombing while American production accelerated. The pilot training disparity compounded numerical disadvantages. By late 1944, German fighter pilots received barely 50 hours of total training before joining operational units. This included basic flight instruction, transition training, and minimal combat preparation. American naval aviators received over 200 hours before carrier qualification, then additional training before joining fleet squadrons. German pilots with minimal experience faced American opponents with 4 times more training, flying superior aircraft in greater numbers, supported by better logistics. The outcome was preordained. No amount of tactical cleverness or individual courage could overcome such systematic disadvantages. The Rechlin test report on the Corsair included remarkably candid strategic assessment buried in technical documentation. The F4U represents American industrial and engineering capabilities applied without resource constraints we face. Its performance exceeds German fighters in critical parameters. Its manufacturing quality demonstrates consistent excellence we can no longer maintain. Its production rates reveal industrial capacity we cannot match. More significantly, it represents a complete weapon system optimized for sustained naval operations over vast distances. Every design choice prioritizes pilot survival, operational consistency, and maintainability. This American approach to fighter design has proven strategically superior to our pursuit of maximum performance. We face an enemy who can afford to build fighters producing over 2,000 horsepower, weighing 14,000 pounds fully loaded, carrying devastating armament, and still produce them in greater quantities than we produce much simpler designs. Combat statistics from the Pacific Theater confirmed what Rechlin testing predicted. Corsairs achieved kill ratios exceeding 10-1 against Japanese fighters. F4U units lost approximately 189 aircraft to enemy action, while claiming over 2,000 enemy aircraft destroyed in air combat. This represented loss rates under 1% per sortie, remarkably low for intense combat operations. The Corsair proved effective in every assigned role: fighter sweep, bomber escort, ground attack, close air support, and even night fighting. Its versatility reflected engineering margin built into the design from inception. The aircraft could be adapted to multiple missions with minimal modification. German fighters were typically optimized for specific roles. The Corsair performed all roles adequately to exceptionally well. 7 of the top 10 Marine Corps fighter aces flew Corsairs during at least part of their combat careers. The aircraft enabled aggressive tactics that leveraged its strengths. Corsair pilots could climb to superior altitude, dive on enemy formations, destroy targets with concentrated firepower, then use superior speed to escape before enemy fighters could respond effectively. The philosophical lesson embedded in the Corsair transcended specific technical capabilities. American designers had created a fighter prioritizing pilot survival and operational consistency over maximum performance. The result was an aircraft that kept pilots alive, remained operational despite damage, delivered devastating firepower, and could be maintained by personnel with basic training in austere conditions. German fighters like the Bf-109 and F4U 190 were optimized for maximum performance from minimum resources. They were brilliant solutions to Germany's specific constraints: lightweight, efficient aerodynamics, powerful armament concentrated in compact packages. But this efficiency came at costs: structural fragility, maintenance difficulty, limited range, combat vulnerability when damaged. The Rechlin test pilots understood these philosophical differences profoundly. They recognized that if Germany could produce Corsairs in quantity with assured fuel and spare parts, The Luftwaffe would adopt them despite their weight and complexity. But Germany couldn't produce such aircraft given its circumstances. German industry struggled to build simpler designs while under sustained bombing. One particularly insightful analysis compared manufacturing requirements. A Bf-109 required approximately 4,000 man-hours to build, representing German industrial efficiency. Rechlin engineers estimated the Corsair required 14,000 to 16,000 man-hours, nearly 4 times the effort. Yet American factories produced Corsairs faster than German factories produced Bf-109s. This revealed that Germany's problem wasn't technical understanding or engineering capability. The problem was systemic industrial capacity. America possessed manufacturing infrastructure, skilled workforce, abundant raw materials, secure factories, and continuous production systems that Germany lacked. Technical excellence couldn't overcome these fundamental disadvantages. The captured Corsair program demonstrated both the value and limitations of technical intelligence in modern warfare. German engineers gained accurate, detailed knowledge through systematic testing and evaluation. This knowledge was valuable and potentially saved some German lives through better tactical preparation. German tactics evolved based on this intelligence, showing measurable improvements when properly implemented under favorable conditions. However, technical knowledge could not overcome strategic-level disadvantages. Germany knew exactly what the Corsair could do. German engineers understood its strengths and weaknesses comprehensively. German tacticians developed appropriate countermeasures based on accurate data, but Germany lacked sufficient competitive aircraft, adequate fuel supplies, enough trained pilots, secure production facilities, or ultimately the time to develop and deploy aircraft matching American high-altitude performance and operational consistency. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.